In this lesson, we're going to talk about the double angle and half angle identities. Using the sum and difference identities as a basis, we can develop the following double angle identities. Sine of 2x is equal to 2 sine x cosine x. Cosine of 2x is cosine squared x minus sine squared x. And tangent 2x is 2 tan x over 1 minus tangent squared. So the way these are developed, I'm just going to do one and you can see how the others come about. So we know, for instance, that sine of x plus y is going to be sine x cosine y plus cosine x sine y. Now, if you think of sine 2x as the sine of x plus x, because 2 times x is just the same as adding it by itself, x plus x. Then you can plug this into your formula for the sum of angles and say sine x cosine x plus cosine x sine x. Both of these terms would evaluate to the same number, so we can simplify this into 2 sine x cosine x. And a similar argument could be made for cosine and tangent as well. I'll leave that to you if you're interested. Cosine 2x is particularly interesting because there's actually some variations there for that one. One variation is cosine 2x is 2 cosine squared minus 1, and the other one is cosine 2x is 1 minus 2 sine squared x. So let me show you how that works. So originally we have cosine 2x equals cosine squared x minus sine squared x. And you could easily see where that would come from if you evaluated cosine of x plus x. So that one makes sense. Now these others, what you can do is work with the Pythagorean identities. So for instance, we know that sine squared x plus cosine squared x is equal to 1, which means cosine squared x is equal to 1 minus sine squared x, and if we go the other route, we could say sine squared x is equal to 1 minus cosine squared x. Those come directly from the Pythagorean identities. If I substitute sine squared x for 1 minus cosine, whoops, 1 minus cosine squared x, then I can say that this is going to be cosine squared x minus that term, because I'm just substituting sine squared for the new values. Alright, so the negative would distribute, and I would have cosine squared x minus 1 plus cosine squared x, or 2 cosine squared x minus 1, which shows me how I get these variations for cosine. And the same would be true, I could get the other variation if I just substituted 1 minus sine squared in for the cosine squared x. So those will become important in a bit. Alright, so let's see how they're used. Let's find the exact value of sine 2x if tangent x equals negative 3/4 and x is in quadrant 4. Alright, so since x is in quadrant 4, I'm going to draw a reference angle in quadrant 4. So this isn't my actual angle, so I'm going to call it like, I don't know, x prime. And that's fine. We can use the reference angle instead of the angle measure itself. So this would be a right triangle, and I know that the tangent of this reference angle is negative 3/4. So tangent is the opposite side over the adjacent side. So what I need to do then is solve for this value right here, which I'll call C, because C is usually the reserved letter for the hypotenuse. Not that it makes a lot of difference. All right, so 4 squared plus negative 3 squared is equal to C squared. So 16 plus 9 is C squared. So 25 is C squared, or C is going to be plus or minus 5, but what we can count on in trig is the length of the hypotenuse always being positive. So positive 5. So I want to know what the sine of 2x is. The sine of 2x I know is going to be 2 sine x cosine x. What I can do now is just substitute in what I know sine and cosine would evaluate to in this triangle in order to evaluate sine of 2x. So sine x would be the opposite over the hypotenuse. Cosine x would be the adjacent over the hypotenuse. So 2 times negative 3 times 4, that would be negative 24. 5 times 5 would be 25. So it looks like negative 24 25ths is the value of sine 2x in that case. All right, find the value of cosine 2 theta, given that sine theta equals negative square root of 2 over 3, and tangent of theta is greater than 0. Okay, so we're not told what quadrant we're in, but we're given kind of some clues. So for instance, all students take calculus. All right, so tangent is greater than 0. So that means we're either going to be in quadrants 1 or 3. All right, tangent is negative in 2 and 4. So we've ruled those out. But we also know that the sine of this angle measure is negative. So that means we're going to be in quadrant 3. So generally you're given some clues as to where things are. Okay, now cosine 2 theta is going to be cosine squared theta minus sine squared theta. So we know what sine of theta is, so we could easily figure out what sine squared theta is, but we'll have to do some work to determine what the cosine squared of theta is. And it comes down to right triangles again. So I know I'm in quadrant 3, so I'm just going to draw a reference triangle in quadrant 3. And I'll just call this theta prime because it's a reference angle. And sine of that angle measure is negative square root of 2 over 3. And that is the opposite side over the hypotenuse. So that means I can figure out what this length is here by doing a squared plus negative square root of 2 squared equals 3 squared. So a squared plus 2 equals 9, or a squared equals 7. So a is either the positive or negative square root of 7. Since I'm in quadrant 3, it's got to be a negative value. Okay, so cosine of 2 theta is going to be, let's see, cosine squared of theta. Cosine would be the adjacent over the hypotenuse. So that's going to be the negative square root of 7 over 3. And then we're going to square that value. Minus sine squared theta, so it's negative root 2 over 3. And then we're going to square that value. So the negative square root of 7 squared just becomes 7 and over 9 minus 2 over 9. So 5/9 is the final answer here. And I don't need to worry about that it's positive or negative. I worried about theta being positive or negative. So the double angle is taken care of through the formula for cosine 2 theta. So it's positive, and that's fine. Next up, show that 1 plus cosine 2x over sine 2x equals cotangent x. All right, well, in order to show this, we start with the side that's most difficult. So I'll begin with the left-hand side of the equation. Definitely some things I can work with there. So for instance, I know cosine 2x could be written as cosine squared x minus sine squared x. And sine 2x would be 2 sine x cosine x. All right, well, let's see what we come up with. So if I take away these parentheses and rearrange some terms, I could write this numerator as 1 minus sine squared x plus cosine squared x over 2 sine x cosine x. The reason I did that rearranging is because this right here, I can use the Pythagorean theorem. Since sine squared plus cosine squared is 1, 1 minus sine squared is cosine squared x. So I'm going to make that substitution. So cosine squared x plus cosine squared x is 2 cosine squared x, then over 2 sine x cosine x. The 2's cancel away. One factor of cosine x cancels out one of these, leaving me with cosine x. So I only have cosine over sine remaining, which is cotangent x. So you can use these for proving identities as well. The next up is the half angle identities. So we have sine of x over 2 equals the positive negative square root of 1 minus cosine x over 2. Cosine x over 2 is the positive or negative square root of 1 plus cosine x over 2. And tangent is similar, but it's basically if you divided cosine, sine of x over 2 over cosine x over 2, this is what you would end up with. Now, these look a little bit strange, but one thing to note is the choice of the sign, even though it says positive or negative, the choice of the sign is determined by the quadrant that x over 2 lies in. So when you determine what angle that quadrant lies in, then you can choose if it's going to be positive or negative. That's all that's really saying. So where do these identities come from? The place where they come from is those variations on the cosine of a double angle. So for instance, we had cosine 2x is equal to, for instance, 1 minus 2 sine squared x. Okay. Now, that particular identity is where this comes from. The way that we do this is first start off solving for the sine of x. So if I subtract 1 from both sides, I would have cosine 2x minus 1 equals negative 2 sine squared x. Then if I divide everything through by negative 2, the negative is going to reverse the order of the numerator because it would make it negative cosine 2x plus 1. So I'm going to write it as 1 minus cosine 2x over 2 equals sine squared x. And now if you take the square root of both sides, you can see that this becomes sine of x equals the plus or minus square root of 1 minus cosine 2x over 2, which you may not think looks exactly right. This is the sine of x and not the sine of x over 2. Well, what you can do is if you let, say, like x equal theta over 2. I'm kind of out of space here. I'll go down a little bit further. And if I let x equal theta over 2, then sine of theta over 2 is the plus or minus square root of 1 minus cosine of 2 times theta over 2 divided by 2, which is what we expect from the formula. So plus or minus 1 minus cosine theta divided by 2. You can do a similar argument for the cosine of a half angle, and if you take sine divided by cosine of half angles, you can get the tangent. So I'm going to save you the proofs there. But half angle identities can be used to expand the number of points where we can evaluate our trig functions exactly. So for instance, let's say we want to find the sine of 112.5 degrees exactly. So 112.5 degrees, that's kind of strange. But if you'll notice, 225 is equal to double that. So for instance, if I divided both sides of this by 2, I could say 112.5 degrees is 225 degrees over 2. So evaluating sine of 112.5 degrees is the same as evaluating sine of 225 degrees over 2. So in order to evaluate that, what we would do is say this is going to be the plus or minus square root of 1 minus cosine 225 degrees divided by 2. Now we have to choose the correct sign. All right, so 112.5 degrees, that's going to be in quadrant 2. Sine is positive in quadrant 2, so we're going to choose the positive. So this is going to just change to a positive because 112.5 is in quadrant 2. So it's going to be the square root of 1 minus cosine of 225. Well, let's grab our unit circle. Here's 225. The cosine is the x value here, so it's negative root 2 over 2. And we really just have to simplify this to get our final answer. So let's see what happens. So this would be the square root of 1 plus the square root of 2 over 2 divided by 2. 2 over 2 plus root 2 divided by 2. So 2 plus the square root of 2 over 2. And instead of dividing by 2, I'm going to think of this as dividing by 2 over 1. I'm going to multiply by 1/2. So this is going to be the square root of 2 plus the square root of 2 over 4. And because you can do the square root of the numerator and denominator separately, I'm going to simplify the denominator and leave this as 2 plus the square root of 2 divided by 2. And that's the simplest form of the answer there. All right, find sine of x over 2 if cosine x equals negative 5/8 and x is between pi over 2 and pi. So if we're between pi over 2 and pi, so here's 0, pi over 2, pi, that puts us in quadrant 2. So the angle measure x over 2 should be in quadrant 1, because if you divide that by 2, so any angle measure that's in quadrant 2, if you divide it by 2, it should be somewhere in quadrant 1. We might not know exactly where, but somewhere in quadrant 1. But regardless, we're looking for sine, and the sine function is positive in quadrant 1. So the final answer is going to be positive. So sine of x over 2. Let's see what the formula tells us to do. So we're choosing the positive. We've already discussed that. So 1 minus cosine x divided by 2. Okay, well, we actually already know what cosine x is. We just need to plug things in. So this is going to be the square root of 1 minus negative 5/8 over 2. And this would become 8 over 8 plus 5/8 divided by 2. So 13/8. Let me write it more like a fraction here. So 13/8 in the numerator. The denominator is 2 over 1, so I'm going to multiply by 1/2. So this is going to become the square root of 13 over 16. And since 16 is a perfect square, I'll go ahead and reduce that. So the square root of 13 over 4. And that's my value. Right? It is possible that you might be asked to solve an identity based off of some half-angle identities. So let's see what that might look like. So we have tangent of theta over 2 is equal to cosecant theta minus cotangent theta. So let's see what that might entail. Well, we do know that it's going to be the plus or minus square root of 1 minus cosine theta divided by 1 plus cosine theta, which I could do some reducing if I multiplied by the conjugate. That's kind of the only thing I can think of at this point. Since I have a binomial, going with the conjugate here. I could maybe split up a fraction, that sort of thing, but I think going with the conjugate's the best thing. Okay, so simplifying that, one thing that I notice is the numerator would become 1 minus cosine theta quantity squared. And I like that because that's a perfect square, and when I take a square root of a perfect square, that can disappear. The denominator would become 1 minus cosine squared theta. And I also like that because that could actually be written as sine squared. So let's do this. Plus or minus 1 minus cosine squared, cosine of theta squared all over sine squared theta. Okay, now the thing that I want you to understand here, any value that we put in for theta is going to result in a positive answer here, because if I put theta into the numerator, if I put any angle measure theta into the numerator, cosine might evaluate to a negative number, but then that's going to get squared. Same thing for the denominator. Whatever I put in for theta, it's going to get squared in the function sine. So everything's going to be positive here. When you take the square root of a positive number, the answer is positive. So I'm going to choose the positive value here. You're based off of this sign right here. I'm going to choose the positive. I'm going to take the square root of the numerator and the denominator, which would be 1 minus cosine theta over sine theta. And now I think I'm almost done. If I split this up, I would have 1 over sine theta minus cosine theta over sine theta. 1 divided by sine theta is cosecant theta. Cosine over sine is cotangent theta. And there I've proven my identity. The most common use of the half-angle identities is through what's known as the power-reducing formulas. That looks like sine squared x equals 1 minus cosine 2x over 2. Cosine squared x equals 1 plus cosine 2x over 2. And tangent squared is 1 minus cosine 2x plus 1 plus cosine 2x. These are used in calculus classes in order to reduce the degree of trig functions from 2 or higher down to 1, which make the operations there in that course much easier. It's not anything that we will use for this course, but I'm putting them here for your reference in case you need them for the future. They're basically, as we were solving for the half-angle identities, we came across this particular step right here before we took the square root of both sides. So it is the same thing as the half-angle identities, just solved and at a different point. But they will become useful later on.